Theory is important, but in my 40 years of working with manufacturers across ASEAN, what matters most is what actually happens on the factory floor. In this final chapter, I'm going to share 3 real case studies: chillers, clean room exhaust air fans, and the flywheel frequency trap, and then give you a practical 4-step action plan you can start implementing this week. Case study 1. A manufacturing plant's chiller system kept tripping during voltage dip events. The chiller itself was robust. The motors were fine. But the control relays in the chiller's microcomputer circuit dropped out at just a 30% voltage dip. The insight: you don't need to protect the entire chiller with a large UPS. You just need to harden the control circuit. Solution: a small voltage dip mitigating device on the control circuit only. Voltage dip testing then confirmed the chiller rides through dips per SEMI F47 at a fraction of the cost of protecting the whole system. Lesson: always identify the actual weak link in the system. Often it's a relay or control board, not the main motor. Targeted protection is far more cost-effective than blanket protection. Case study 2. A semiconductor cleanroom's exhaust air fans, driven by VSDs, were tripping during voltage dips. Auto restart meant the fans came to a complete stop before restarting, causing air pressure to drop to 0, triggering alarms and product scrapping. The solution cost nothing. The VSD supplier confirmed the drives had a built-in flying restart function. Enabling this allows the VSD to catch the spinning motor mid-coast and accelerate it back to speed without ever reaching 0 pressure. But here's the expert-level warning. If you enable flying restart on all drives simultaneously, the aggregate inrush current, when they all restart at once, can trip your upstream breakers. The correct strategy is delayed staggering. Critical drives, like exhaust air fans, restart immediately. Secondary drives follow with 5-minute, 10-minute delays. This smooths the I²T inrush curve and prevents a secondary outage caused by your own recovery. Case study 3 is a cautionary tale. A customer had multiple flywheel UPS units that had successfully handled dips as severe as 7 to 8%. Then one day, a minor 3% voltage drop from a power generation fault caused all their flywheel units to activate simultaneously. Because the grid frequency briefly dropped to 49.3 Hz, below the OEM's factory set 49.5 Hz threshold. The flywheels disconnected the grid. Their stored energy depleted. The plant went dark. The fix: adjust or disable the frequency threshold on the flywheel UPS because their equipment was not frequency sensitive. This is why a DYSC is structurally more resilient in Singapore's manufacturing environment. Voltage threshold activation only, no frequency trip risk. Planned risk assessment. Map your critical processes and use historical PQ data. Do implement solutions. Specify Samsung Power Vaccine for new equipment or deploy DYSC for existing assets. Check. Monitor and evaluate. Install permanent Class A IEC 61000-4-30 monitors. Act. Review and improve. Analyze PQ trends and fine-tune VSD restart strategies based on real incident data. That wraps up our 5-chapter series on mastering voltage dip management. We've covered the fundamentals, precision monitoring, the 5-tier protection hierarchy, DYSC technology, and real-world case studies. The full technical white paper this series is based on is available. Link in the description. Download it, share it with your M&E consultant, and use it to start your PDCA review. If you protect manufacturing, this channel is for you. Subscribe. See you in the next series.